Hello. Today, the learning objective is about phase rule. To study the behavior of heterogeneous systems, phase rule was proposed by Willard Gibbs in 1874. So, the phase rule generalization it was given by J.W. Gibbs in 1874. Further, this was studied by H.W.P. Roosbaum in 1884. So this phase rule it is able to predict the conditions necessary and they are specified for the heterogeneous system to exhibit the equilibrium. This phase rule helps in studying heterogeneous equilibrium systems with two or more phases in equilibrium. So what is a phase? What are the examples? What is a component? What are the examples? What is degrees of freedom? What is Gibbs phrase rule? We'll see. So here the heterogeneous system, how it's exhibiting the equilibrium is studied under this phase equilibrium. Study of chemical systems, study of chemical systems, usually we deal with the systems containing two or more phases in equilibrium. These are called as the heterogeneous systems or polyphase systems. Phase rule was based on basis of the principles of thermodynamics. So the phase rule it is able to predict the quantitatively about the means of the diagram, the how a temperature is changing, pressure, concentration on and how it is affecting on a heterogeneous system which is in equilibrium. In this chapter, we'll discuss about the phase rule, various applications in the daily life. Gibbs phase rule. What is the rule? What was the rule that was proposed by Gibbs? Phase rule can be defined as when a heterogeneous system in equilibrium at a definite temperature and pressure, the number of degrees of freedom it is equal to 2 the difference in the number of the components and the number of phases provided the equilibrium is not influenced by the external factors such as gravity, electrical or magnetic forces, surface tension, etc. So, simply, how we define the Gibbs phase rule? The phase it is denoted by P, component by C, degrees of freedom by F, and what is the Gibbs phase rule? The sum of Gibbs phase rule. The sum of number of degrees of freedom and the number of phases exceeds the number of components by 2. Okay, number of degrees of freedom and number of phases exceeds the components by 2. F plus P is equal to C plus 2. F is equal to C minus P plus 2. F is the degrees of freedom. C is the number of components. P is the number of phases of the system. For understanding various applications of phase rule, for understanding various applications of phase rule, a clear understanding of various terms that is phase P, components C, degrees of freedom F, which are present in the phase rule, it is essential for us to get the specific meanings. So F plus P is equal to C plus 2 or F is equal to C minus P plus 2. Now, what is a component? So, what is a component? Minimum number of independently variable constituents in terms of which the composition of each phase of heterogeneous system can be expressed directly or in the form of chemical equation are called as the components of the system C. I'm repeating, minimum number of independently variable constituents in terms of which the composition of each phase of heterogeneous system that can be expressed directly or in the form of chemical equation are called as the components of system. That is called as the components of the system. It is denoted by C. Let me give you a clear-cut exam meaning for this one. It is denoted by C. Now, number of components in a system, it is the smallest number of independently variable constituents by means of which composition of every possible phase in the system can be expressed with a chemical formula. It can be expressed with a chemical formula. So the number of components in a system is smallest number of independently variable constituents by means of which the composition of every possible phase in the system is expressed with a chemical formula. Example, you can take water. It has three phases. So the composition, the formula is the components. The formula is nothing but the components. Yeah, a system, it is containing solution of sugar in water. So the phase is one, solution phase, but the components are two, sugar plus water. So it is a two component system. The solution phase consists of two constituents. Number of constituents in a phase is component. Number of constituents in a phase is nothing but a component. Sugar solution, water plus sugar. We can take some of the examples. Here, ice, it is in equilibrium with water, water in equilibrium with vapor. So the system consists of three phases: ice, water, water vapor. The chemical substance present in each phase is water. Here, ice, formula is H2O. Water, the formula is H2O. And vapor, again the formula is H2O. So whatever is the phase, but the formula is the same. So therefore, the three phases have the same formula, same composition, that is components, that is H2O. Therefore, composition of each phase is expressed in terms of water. Therefore, it is called as one component system. Therefore, it is called as one component system. You can take an example of saturated solution of sodium chloride. It consists of three phases. It is having three phases. Solid sodium chloride, salt solution, water vapor in the equilibrium, all these. See, NaCl solid in equilibrium with NaCl aqueous. It is in equilibrium with water vapor. Similarly, you take calcium carbonate. That's solid. It is in equilibrium with calcium oxide and carbon dioxide gas. The chemical composition of each phase of the system expressed, if you consider two component system, NaCl and water, the components are two, the phase is one. NaCl solid, the phase is solid. Components you'll be having for the solution, NaCl and water. If it is solution, You have NaCl and water. NaCl aqueous, NaCl plus H2O. The components are two. The phase is 1. So NaCl solution, NaCl plus H2O. NaCl aqueous solution also, NaCl plus H2O. Only water gas, it is NaCl plus water. So if it is in gaseous phase or solid phase or it is in aqueous phase, whatever it may be, the components are two. So it is a two component system. If the components are one, then that is one component system. If it is two, it is two component system. You take copper sulfate solution. CuSO4 in equilibrium with CuSO4, 3H2O, 3H2O plus H2O gas. Here you can see three phases, but the components, the formulas are only two. The formulas are only two, CuSO4 and H2O. Only two you are having. Okay, so this is the component. The number of formulas, the number of components is component. Similarly, we take a sulfur system. Yeah, I'm giving some more examples. Sulfur system. It is having monoclinic, rhombic, plastic, vapor, all the four phases, but composition is only sulfur. Similarly, you can take a calcium carbonate, as previously this is the example. For that example, each phase you're having that calcium carbonate, calcium oxide and carbon dioxide. In this system, each phase can be expressed with two constituents. Similarly, ammonium chloride, ammonia plus HCl. In a closed vessel in the gaseous phase, NH3 and HCl are always in equal amounts. Hence, composition of two phases are expressed in single component, NH4Cl, C is equal to 1. Yeah, in an open system, you take NH3 and HCl, they are in equal amounts. The number of components are C is equal to 2. You can take an example of sodium sulfate water system. They are also here. You are having solid ice, water, water vapor, whatever. So solid sodium sulfate and water. The composition, it can be expressed with two chemical formulas. Sodium sulfate and water system, how many ever may be the phases? Different phases are there. I think you can see about 7 phases in sodium sulfate and water system. But the composition, wherever you go, wherever you see the phase of the sodium sulfate and water, we can get only two. It's a two component system. It's a two component system. Next, let us see degrees of freedom. The next term, what is the degrees of freedom? The smallest number of independently variable factors such as temperature, pressure, concentrations, which must be required in order to define the system, which are required to define the system, completely are called degrees of freedom. They're called as the degrees of freedom. Degree of freedom is known as variance. Degrees of freedom is known as variance. The smallest number of independently variable factors, the smallest number of independently variable factors such as temperature, pressure, concentration, which are required in order to define a system, completely are called degrees of freedom. Nothing but variance. So a system has no degrees of freedom, F is 0, non-variant system. If there are no factors that are governing, if there are no factors for the system, then that there is a zero variant or non-variant system, invariant system, non-variant or invariant system. Smallest number of smallest number of independently variable factors such as temperature, pressure, concentration, which are required in order to define the system completely, are degrees of freedom. Next, coming to when a system is having only one degree of freedom, that is univariant or monovariant system. It is a univariant or monovariant system. Coming to the another system, 2 degrees of freedom. Next, if F is 2, it is the bivariant system. The term degrees of freedom can be understood with the help of the following examples. The temperature, pressure, the system is in equilibrium with water, water in equilibrium with vapor. It has no degrees of freedom. If it has no degrees of freedom, F is equal to 0. So there are 3 phases of water: ice, liquid, water, and water vapor. So all these exist in the equilibrium only at particular temperature and pressure. So corresponding to the freezing point, and no factor is necessary to be specified to define a system. So a system, if it's consisting of ice, water, and vapor in the equilibrium, it has no degrees of freedom. It is a non-variant system. It is a non-variant system. For a mixture of gases, the number of degrees of freedom is 3. F is equal to 3. Such a system can be completely defined when temperature, pressure, composition. Next, these are all fixed. In this case, here, and a system consists of ice, water, and water vapor in equilibrium. It has no degrees of freedom and it is a non-variant, as I've told you. For a mixture of gases, the number of degrees of freedom is 3, then F is equal to 3. Such a system can be completely defined when the temperature, pressure, composition are fixed. In this case, the remaining factor, that is volume, gets automatically fixed. A gaseous mixture you take, it is 70% N2, 30% of O2 at 22 degrees centigrade, and 1 atmospheric pressure. So it is completely defined that it doesn't require any other information for this description. So the system, it has 3 degrees of freedom. The 3 degrees of freedom, that is trivariant system. It is the trivariant system. So for the mixture of gases, if you take the 3 components, the number of degrees of freedom is 3, then it is trivariant system. Such type of example is here, which I have told you. So it is dependent on temperature, pressure, composition, and these are fixed. In this case, the remaining factor, volume, gets automatically fixed. So the gaseous mixture, it's containing 70% N2, 30% O2 at 22 degrees and 1 atmosphere. See here, the temperature dependent and atmosphere. And the volume, it's getting automatically fixed up. So whatever it may be, the system, it is having 3 degrees of freedom. One is the volume, the other one is the temperature, and the third one is the pressure. So it is a trivariant system. You are having a volume, you are having temperature, you are having pressure. So the 3 governing factors, the F is degrees of freedom is 3. F is equal to 3, trivariant system. Now we'll see another example. For a saturated solution of lithium chloride solution, the number of degrees of freedom is 1. Saturated lithium chloride solution. We are talking about the components is lithium chloride solution. Lithium chloride is one component, water is the other component. Yeah, we are not talking about the components. The component C, it is two. One is lithium chloride, the other one is water. So here we are discussing about the degrees of freedom. The degrees of freedom, it is one because the system is completely defined at specifying temperature only. The two other factors, that is composition and vapor, automatically they are fixed. So when the temperature is fixed, a system it consisting of saturated lithium chloride, it is univariant. It is univariant. So we are specifying only temperature. So F is equal to 1 and it is univariant system. Let us see derivation for the phase rule equation. Gibbs phase rule can be derived on the basis of thermodynamic principle. Now, basing on the thermodynamic principle, this phase rule was defined for us. So the number of degrees of freedom of a system is the number of the factors, namely temperature, pressure, concentration of the components, which can be changed without altering the number of phases. That is the degrees of freedom. Now, basing on the degrees of freedom, that is F, basing on components, basing on the phases, let us see the phase rule. What is the phase rule equation? How the Gibbs has derived it. See here, Gibbs phase rule, it can be derived on the basis of the thermodynamic principle. So considering a heterogeneous system of different pressures, different phases and different components, and non-reacting mixture is taken. There is a passage of the component from one phase to another phase and doesn't involve any chemical reaction. So when such one system is in equilibrium, it can be completely specifying the following variables: pressure, composition, and temperature. So total number of variables specifying state of system is temperature, that is same for all phases, pressure, same for all phases, and concentration. So independent concentration variables for one phase with respect to C. So C minus 1. Therefore, concentration of the last component, it is independent. Independent concentration variables for phases with respect to C components is with respect to P, it is P into C minus 1. Independent concentration variables for one phase with respect to C is C minus 1. And with respect to pressure and C components, it is P into C minus 1. So total number of variables is P into C minus 1 plus 2. Okay, so the total number of equilibria. See, for one component, chemical potential is mu. There in the equilibrium, the chemical potential is mu for each component. So mu1 into P1. Again, this is equal to mu1 into P2, mu1 into P3, mu1 into P, so on for component 1. Similarly, the chemical potential into P1, chemical potential 2 for component 2. The chemical potential is mu2, mu2 into P1, mu2 into P2, mu2 into P3, mu2 into P, so on. Similarly, mu into C, P1, mu into C, P2, mu C, P1, mu C, P, so on. So for each component of the equilibrium, P phases, P is P minus 1. For C components, the number of equilibrium for P phases are C into P minus 1. So total number of equilibria involved, E, is equal to C into P minus 1. So from equation 1 and equation 2. Equation 1 and equation 2. Okay, so here, this is the one and this is 2. You get F is equal to P into C minus 1 plus 2 minus of C into P minus 1. So F is equal to here, PC minus P plus 2 minus Cp plus C plus C. Therefore, C into C, C into 1, C. So minus into minus plus. F is equal to C minus P plus 2. F is equal to C minus P plus 2. So this is the Gibbs phase rule equation. So total derivation of the formulas, you get it. Okay. Next, here are the conclusion for the phase rule equation. For a system, it is having specified number of components. The greater is the number of phases, lesser is the number of degrees of freedom. The components are specified. More are the phases, less are the degrees of freedom. C is equal to 1, P is equal to 1. So according to phase rule, F is equal to C minus P plus 2. This is equal to 1 minus 1 plus 2 is equal to 2. The system has 2 degrees of freedom. The system is having 2 degrees of freedom. Okay, F is equal to C minus P plus 2. This is equal to 1 minus 2 plus 2 equal to 1. Monovariant system. Next, a system, it is having number of given number of components and the maximum possible number of phases in the phase equilibrium. It's not variant. One component system, maximum possible number of phases is 3. For one component system, possible number of phases is 3, solid, liquid, gas. One component system, it has 3 phases in equilibrium. It has no degrees of freedom or non-variant. For a system, it is having a given number of phases. So the larger the number of components, greater is the number of degrees of freedom of the system. So one component system, you take C is equal to 1, C will be 1 component, and phases will be 2. So the formula is F is equal to C minus P plus 2. So this is equal to 1 minus 2 plus 2. This is equal to 1. Therefore, this is one component system. F is equal to 1. It is one component system. For two component system, C is equal to 2, P is equal to 2. What is the phase rule? F is equal to C minus P plus 2. C is 2, P is 2. 2 minus 2 plus 2, you will get 2. It will be bivariant system. The two component system has greater number of degrees of freedom when compared to one component system. Now we'll see how the phase diagrams, how can it be classified. And now each class will discuss how they are phase diagrams. The graphical presentation gives the conditions of pressure. See, a graph will be there is a graphical representation. It gives the conditions of pressure, temperature, under which the various phases are existing and transform from one phase to the another phase. This is known as phase diagram of the system. A phase diagram, it consists of the areas, curves, lines, and points. So the graphical representation, it's giving the condition of the pressure and temperature under which the phases are existing. And what is the transformation is going on from one phase to another. This is the phase diagram. So you can better understand what is a phase diagram. How the phases are changing with respect to the pressure conditions and temperature conditions. All these are represented in a diagrammatic way. That is a graphical representation. It is called as the phase diagram. And in this phase diagram, you get areas, curves, lines, points. And for each system, we need to discuss about the areas, about the curves, lines, and points. Now we'll see what is a phase diagram, how it is being classified. Phase diagram depending on the component present in the system. For one component system, it is water system, example. If it is two component system, there is a classification. Now, component which reacts to form compounds. Component which reacts to form compounds. Components which are completely miscible but do not react. Okay, for two component system, which react and which do not react. and the component system which reacts to form the compounds are again of two types: the system with congruent melting point, the system with incongruent melting point. Yeah, let us discuss in detail with each system in the further classes. Next, the component which reacts to form compounds. System which is having congruent melting point, that is the zinc and the magnesium system. Next, the system which is having congruent melting point, sodium potassium system. The system which is having incongruent melting point, that is sodium and potassium system. Under reacting component systems, one is congruent, the other one is incongruent. Congruent is zinc and magnesium. Incongruent is potassium and sodium. Next, the compounds which are completely miscible and which do not react are eutectic mixture, lead silver system we can take. They don't react. The system don't react. These two components don't react. Now, what are the phase rule for one component system? Yeah, in later classes, we'll see about the now phase rule for one component system. The least number of phases possible in a system is 1. So according to phase rule equation, one component system should have maximum of 2 degrees of freedom. C is equal to 1, P is equal to 1, F is equal to C minus P plus 2. So 1 minus 1 plus 2, this is equal to 2. So hence one component system requires maximum of 2 variables to be fixed in order to define the system completely. The 2 variables are temperature, pressure. So the phase diagram for one component system can be obtained by plotting with pressure versus temperature. In case of one component system, in case of one component system, phase diagram, it is having area, curves, lines, and points. This provide the complete information regarding the system. One in case of one component system or two component system, whatever you take. It consists of areas, curves, lines, and points. This provide the following information. Points on the phase diagram. What it represents? Invariant or variant system. That can be discussed. A point generally represents non-variant system. And the areas represent bivariant system. And the areas represent the bivariant system. Curve or a line, it represents a univariant system. Curve or a line represents a univariant system. So water system and the sulfur system are the examples of one component system. Because H2O is a formula for water system, sulfur S is the uh, formula for the sulfur system. Yes. Now, we'll see generally the examples for all the systems. Water system, we'll see. Water system, how it is changing, what are the curves, what are this, how it's taking place, we'll see. Yeah, a brief discussion I'm going to give you. And in later class, I'll explain in detail about all the systems. Water is one of the system which is chemically a single compound involved in the system. The three possible phases in the system are ice, solid phase, water, liquid phase, and vapor, that is the gaseous phase. Hence, water consists of three phases. One component system is the water is three-phase system. It has the following equilibria: ice in equilibrium with water, ice in equilibrium with ice in equilibrium with vapor, ice in equilibrium with water, water in equilibrium with vapor. So the existence of this equilibria at particular stage depends upon the conditions of temperature, pressure. With these are the variables of the system. If the values of the vapors are at different temperatures and plotted against the corresponding temperatures, the phase diagram of the system can be obtained. Phase diagram of water system, it is shown. Yeah, coming figure, I'll show you. The explanation of the phase diagram of water system can be as follows. Here, you are having these are the phases. This is the triple point CO, OB, OA. Pressure is on the y-axis, temperature on the x-axis. See how these are changing. OA, OC, OB. The curves, here you're having OB curve, curve OA, areas AOC, COB, BOA. And you can see salient features of this water system, how it is changing. Water, one component system, it is chemically and single compound involved in the system. The three possible phases in the system are the ice, that is solid, water, liquid phase, vapor, gaseous phase. Hence, water constitutes a three-phase, one component system here, and three types of equilibria. The existence of this equilibria at particular stage, it depends on the conditions of the temperature, pressure. Different vapor pressures at different temperatures are plotted. Here, curves. We'll see OA curve, the OB curve, OB curve, and OC curve, and OA curve. See, OB curve is known as the vapor pressure of water, and it tells about the vapor pressure of water at different temperatures. Along this curve, you're having water and vapor exists in equilibrium. The water vapor of the water becomes equal to the atmospheric pressure 100 degrees, represents boiling temperature 100 degrees, and boiling temperature of water. Curve OB. OB finishes at B, where the liquid water are indistinguishable and the system has only one phase. The point is called critical point. This point is called critical point. So C is equal to 1, P is equal to 2, PF is equal to C minus P plus 2, and 1 plus 2 minus 2 is equal to 1. Hence the curves represents univariate. This explains that only one factor to be fixed definite system. Similarly for the curve OB, it is a sublimation curve of ice. Gives the vapor pressure of the solid at different temperatures. Along the sublimation curve, two phases ice, water vapor exist together in the equilibrium, and the lower end of the curve OA extends to about 0, minus 273, where no vapor exists. And let us go on for the areas. AOC, COP, and BOA. AOC, COP, and BOA. AOC, COB, AOC, COP, and BOA. So here ice, water, water vapor. ice, AOC, AOC ice, BOC water, BOA water vapor. Okay, so these are the phases that exist. For every area, the C is only one H2O, and P is one, phase is only one. So applying the phase rule, you get F is equal to C minus P plus 2. This is equal to 1 minus 1 plus 2 equal to 2. For areas, you get bivariant system, and for the curves, we get univariant system. Here are the salient features. So hence, this binary system, it becomes specified. Both temperature pressures define one phase. We'll see here curve OB, curve OA, curve OC, curve OA prime. Sublimation curve, vaporization, fusion, metastable vaporization curve. Metastable vaporization curve. Here these are the phases. Liquid and the vapor are there in between OB. Solid and vapor are there between OA. Solid and liquid and vapor. And the number of phases are all 2 and univariant. For the curves, it is univariant. Yeah, for areas, only one phase. Okay, bivariant system. So it is a bivariant system. Say OA, OB. This is the vapor pressure curve. This is the fusion curve. This is the sublimation curve. And this is the metastable curve. This is the triple point. Now you know. For these curves, you're having the univariant system. And for this areas, you're having bivariant system. And non-variant system for O. So, and the salient features for this water vapor is given as follows. I hope everybody have understood today's class. What we have discussed is about the phase rule. We have discussed about the phase rule. Yeah. Gibbs phase rule. What is a component? What is degrees of freedom? What is a phase rule? How we have got the derivation? What is a phase diagram? What is a classification? And under this, we have seen one component system, that is water system. And we have drawn the diagram, you have seen the diagram. What are the to be discussed curves, OA, OB, OC, OC prime, and what are the areas? What is a triple point? I hope everybody have understood today's class. Thank you.